Welcome students. We are back with another lesson. In this lesson we'll continue with the energy level diagram of hydrogen atom and then we'll discuss the excitation energy and the ionization energy. So up till now we have discussed about your Bohr's atomic model. According to the Bohr, an electron, this blue one, this electron has to revolve in a discrete and a distinct value of the orbit. Let us say this is the first orbit, n equals to 1 orbit. This is your second orbit, n equals to 2 orbit. This is your third orbit, n equals to 3. Fourth orbit, n equals to 4. Fifth orbit, n equals to 5. Sixth orbit, n equals to 6. Seventh orbit, n equals to 7. Eighth orbit, n equals to 8. Ninth orbit, n equals to 9, and so on. So the point here is that this electron has to revolve in a discrete value, that means distinct value. It cannot exist somewhere at 9.5, 8.5, 2.3, 4.1. The electron cannot exist between two states. It has to be either in the lower state, like in this case, either it has to be in the 8th state or it has to be in the 9th state. It cannot exist between any of these two states. Now after this we have discussed the spectral series of the hydrogen atom. Here the electron revolves in a discrete orbit. Now let us suppose if your electron is in the second orbit. If it makes a jump from the second to the first orbit, then it releases some energy. Check again. If it makes a jump from the second to the first orbit, can you see the purple light which just came out? That is a form of a energy radiation. So what we do is we will obtain that energy radiation on a black screen. That is a type of a emission spectra which you'll study in the higher classes. For now you consider like this. When an electron is in the second state, when it makes a transition to the first state, it releases some energy. Similarly, if the electron is in the third state, n equals to 3 orbit, third orbit, and if it jumps to the first orbit, it releases some energy. Similarly, if it is in the fourth orbit and it makes a transition to the first orbit, it again releases some energy. Similarly, if it is in the fifth orbit, it releases some energy. Now the energy produced is a wave, and that wave has a wavelength somewhere around 94.9 meter when the electron jumps from the fifth to the first orbit. If the electron jumps from the second to the first orbit, in that case the wavelength is around 121 nanometer. If the electron jumps from third to the first orbit, in that case the wavelength is how much? 102. If the electron jumps from fourth to the first orbit, in that case the wavelength is 97.2. If the electron jumps from fifth to the first orbit, again the energy produced will be of the wavelength 94.9 nanometer. So in all the cases you saw this wavelength was approximately close to 100 nanometer. Fine. When the electron made the transition from 2 to first, it gave energy in the wavelength of 121.6. And if you recorded that energy on the black screen, you will obtain 121.6. You will obtain this line. Fine. When the electron has made the transition from the second to first. When the electron makes a transition to 3 to 1, in that case, the wavelength produced will be of the wavelength 102.6, somewhere around here. Fine. Similarly, when the electron makes a transition from 4 to 1, it produces energy of wavelength 97.2, somewhere around here. Similarly, if it is 5th to 1, then it produces energy 94.9, somewhere around here. So in all of this case, where the electron makes a transition from a higher state 2, 3, 4, 5 to a lower state 1, in that case, it gives the energy which falls in the ultraviolet region. So such kind of transition from 2 to 1, 3 to 1, 4 to 1, 5 to 1, such kind of spectral series. Okay, the spectrum, this is your spectrum. Okay, this is the series of spectrum. So this type of series will be known as your Lyman series. Fine. Similarly, the next one is your Balmer series. The electron will make a transition from 3 to second orbit. Can you see it produces a red light? Similarly, consider this one. When it makes a transition from a 4th to second orbit, it produces somewhere around blue light. When it makes a transition from 5th to second orbit, it produces somewhere around a purple light. Okay, so in the case when the electron makes the transition from third orbit to your second orbit, it gives the radiation of wavelength 456 nanometers. Okay, somewhere around here it gave a this kind of a purple light when the electron made the transition from fourth to the second orbit. Okay, this 616 nanometer, it gave somewhere around somewhat about a light blue radiation. This one, when the electron made the transition from fifth to the second orbit, it produced a red color light like this one, whose wavelength is 690.7. So in such kind of transition, where the transition is from the third to the second orbit, fourth to the second, fifth to the second, that means from any higher state 3, 4, 5, 6 and so on to n equals to 2 orbit. Okay, in this case, whenever electron makes up transitions, it gives energy which falls in the region of the visible light. This visible light is what we can see from our normal human eye. Okay, and this spectral series was discovered first out of all this series, out of all Lyman series, Paschen series, bracket series. It was discovered first. Why it was discovered first? Because it was observed by our normal human eye. This kind of spectral series we require sophisticated equipments, but for this kind of series we can see the series from our normal human eye. Why? Because they fall in the visible region. Okay, so in such kind of series where the transition is from higher state to n equals to 2 state, your second orbit, such kind of spectral series will be known as your Balmer series. Fine. Now the rest kind of series is your Paschen series, where the electron makes a transition from the higher excited state to n equals to 3 orbit, that is to the third orbit. Such kind of series is your Paschen series, and the energy produced will fall under infrared region. Similarly, when an electron makes a transition from a higher state to your fourth orbit, n equals to 4 state, in that case the spectral series will be known as your bracket series. Again, in this region the emitted radiation will fall under infrared region. Similarly, the final one is your P1 series. When the electron makes a transition from a higher excited state to your fifth excited state, your fifth orbital, in that case such kind of series will be known as your P1 series. Fine. So we have discussed the various type of spectral series: Lyman series, Balmer series, Paschen, bracket, P1. Fine. Now after discussing the various type of spectral series, what we have discussed is that how much will be the energy of the electron which revolves in that specific orbit. So if you look here again, we have derived if the electron is in the first orbit, n equals to 1 orbit, the energy it will have is minus 13.6 electron volt. Here we have derived the energy of the electron in the first orbit is how much? Minus 13.6 electron volt. Similarly, we have derived for the electron in your second orbit, minus 3.4, in the third orbit, minus 1.51, for the fourth orbit, minus 0.85, for the fifth orbit, minus 0.54, for sixth orbit, minus 0.37. So we had derived if the electron is in the first orbit, n equals to 1 orbit, how much energy it has? Minus 13.6 electron volt. Then for the electron which is in your n equals to 2 orbit, we have found that the energy of your second energy of the electron in your second orbit should be how much? Minus 3.4 electron volt. For n equals to 3, electron in your third orbit, here how much energy this electron should have? It should have minus 1.51 electron volt. If it is in the fourth orbit, then the electron should have minus 0.85 electron volt. And from the fifth orbit, it is minus 0.54 electron volt, and so on. Fine. So this is what we have derived so far. Now if there is an electron, okay, and suppose if your energy is in the ground state means this n equals to 1 orbit, then how much energy is required by this electron to jump from the ground state to a higher excited state, n equals to 2 orbit? The energy required is known as your excitation energy, right? Similarly, if this is your electron and if I want to make this electron revolve at your third orbit, then how much energy has to be supplied is known as your excitation energy. So the excitation energy is defined as the energy required by an electron to jump from ground state to any one of the excited states. And suppose if I want to make a jump from the first orbit to the second orbit, what you have to do? You have to calculate the difference between these two energy levels. So how much is the energy level for the electron in the second orbit? It is minus 1.51 electron volts. And in the first order, n equals to 2 orbit, it is minus 3.4 electron volts. Okay, this is for n equals to 2. And for n equals to 1, the energy is minus 13.6 electron volts. So the difference of these two energies, E2 minus E1, which is around how much? 10.2 electron volts. This is the amount of the energy which you need to supply in order for the electron to jump from ground state to the higher excited state. Similarly, this is known as your first excitation energy. Now similarly, if I want to make a transition from the first orbit to the third orbit, then again also I have to supply some energy to the electron. Now if I supply that energy, how much should be that energy? The energy should be the difference between the energy of the third orbit minus the energy of the first orbit, which is 12.09 electron volts. So if I supply 12.09 electron volts, what will happen? The electron which is revolving in the n equals to 1 state now will move to n equals to 3 state. Fine. So the energy difference is 12.08. Okay, it's somewhere close to 12.09. So you have to supply this much amount of energy in order for the electron to jump from n equals to 1 to n equals to 3 state. So such kind of energy where you want to make the electron jump from the ground state n equals to 1 state to higher states. Such kind of energy is known as your excited energy. Okay, the next energy is your ionization energy. Now suppose if I want to completely remove this electron from this atom. What do you mean by this? Suppose if I supply so much energy that this electron is completely knocked out of atom. Okay, now this amount of energy required to knock an electron completely out of atom is known as your ionization energy. So it is defined as the energy required to completely knock the electron out of atom. Okay, and the energy, ionization energy for the ground state will be how much? 13.6 electron volt. So if you supply a amount of energy, how much? 13.6 electron volt, the energy will be completely the electron will be completely removed from that atom, right? So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I will re-explain it to you again. So again, thank you.